Have you ever sat in math class and you've been learning something and you thought, come on, I am never going to use this? I feel you. I've thought the same thing. Mathematicians have never much cared, frankly. They've always just thought, you know what, math is beautiful, I'm going to do it anyway. But a strange thing is true about the history of the world and math, which is very often we develop really cool math equations that don't serve any purpose, and then they turn out to be just what physicists need to describe the world. One cool example of this is projectile motion. In projectile motion, we look at something called a parabola. Maybe you remember it. Well, parabolas were studied by the ancient Greeks around 400 BC, and there was no particular use for them. But 1900 years later, Galileo put them to use to track the motion of things in the air, projectile motion. And that happens over and over again. So let's take a look at projectile motion with this one particular math formula, the parabola, and think about how it can help us solve these problems. Let's dive in. Let us begin with our lesson objectives. First, we'll use parabolas to explain projectile motion. It turns out we can map out the path of a projectile with a parabola. Then we'll introduce the quadratic equation. Perhaps you remember this from math class. It allows us to solve for what's called the zeros of a parabola. And that will be used here in our projectile motion. Then we'll practice solving a projectile motion problem with the quadratic equation. The problem we'll solve is from the TEAS physics textbook. That's a free online textbook that you can just Google and have access to. All right, let's look at the path of a projectile. Here we have a cannonball flying through the air. What mathematical function describes this path? Well, it might take a second to see because this is actually upside down compared to how you're usually used to seeing them, but it's a parabola. So projectile motion is well described by a parabola. And like I said, it's an upside down parabola. So you're used to seeing this flipped around, but we can flip it either which way. And the upside down parabola is what matches projectile motion. Just a couple important points here on our parabola. The top here is our maximum height. Do you remember what our velocity in the y direction is at the maximum height? It's 0. That's because it's going up, and then it pauses, and then it returns back down. So at its maximum height, the velocity in the y is 0. Then we also have what's called the x-intercepts, or the zeros of this parabola. And that's actually what's going to be solved for by the quadratic formula by realizing that at this point, y equals 0. So when we use our quadratic formula, we'll always set everything in the equation for the parabola equal to 0. All right, now let's actually imagine our cannon and this parabola together. It might look like this. So notice that our parabola is usually truncated. That is, we kind of chop it off at some point. Basically, the reason here is that at the beginning of the problem, our cannonball may not be fired. It's just kind of chilling in the cannon. And so we're not ever really going to consider the left half side of that parabola. It just starts in the cannon and then makes a portion of that parabola. So when we look at this full parabola, which of these x-intercepts would never be touched by the cannonball if it was fired like we showed before? Well, clearly this one. That never happens. And actually, it's not uncommon to get a negative answer when we do the quadratic formula. We'll get one positive and one negative, and we just actually throw out that negative answer because it doesn't actually happen in the physical world. So, only one x-intercept typically represents motion. How do we find those x-intercepts? Well, remember that the general form for our parabola is y equals ax squared plus bx plus c. Here's the thing, is that a is always going to go with the x squared, and the b with the x, and the c will have no x's on it. That's really important. When we set all of that equal to 0, we can use the quadratic equation. Perhaps you remember this. It tells us x equals negative b plus or minus square root b squared minus 4ac all over 2a. In fact, you may have learned a fancy song to remember this. I sure did. Let me sing it. Okay, on second thought, I'm going to let my wife sing it because she can actually sing. Here, Chelsea, you sing.
Negative b plus or minus square root plus or minus square root b squared minus 4ac, b squared minus 4ac, all over 2a, all over 2a.
Thanks, Chelsea. All right, back on to our physics lesson. So here are our 2D projectile motion equations. What I want you to ask yourself is which one of these looks like a quadratic function? There's kind of two options. Only two things have squared things floating around, but it's this bottom one that matches the parabola. And do you see that negative sign in front of the minus 1/2 gt squared? That's what makes our parabola upside down, because the gravity is pulling that object down the whole time. And so the x's here have actually been replaced by t's. And so when we think about projectile motion, we could think about the x position, that is the horizontal position, or we could think about time. And both of them follow that same function. All right, let's look at a problem we can solve with the quadratic equation. This problem tells us that a large rock is ejected from a volcano at 25 meters per second at an angle of 35 degrees. The rock lands 20 meters lower than its starting point. How long does it take the rock to reach this point? Well, recall that the first thing we want to do is draw the circumstances so that we can identify all of our different variables. Here we have the y direction in the vertical and the x direction in the horizontal, just as typical. One really important thing to note is that we're thinking about that rock falling 20 meters below where it started. So we're going to set the top of the volcano equal to 0. That's 0 height. And the rock is eventually going to end up at minus 20 meters. Okay, with this picture in mind, let's actually solve it. Now that we've seen a good picture of what this problem looks like, we've basically drawn it. So we'll go to our step 2 for projectile motion problems, which is to split up our velocity into its components. Since we want to know about how low down this rock reaches, that's a question about the y direction. And so we're going to go ahead and solve for our velocity in the y direction. The velocity in the y direction initially is equal to our velocity initial times sine of theta. And so in this case, we're going to plug in for our velocity initial that 25 meters per second and multiply by sine of the angle we're given, which is 35. When we do that, we'll get our velocity y initial, and it turns out that that's 14.3 ... meters per second. So we want to keep all of that in our calculator. What else do we know? Well, we know that the initial displacement we've defined as 0. And we also know that eventually it's going to be below that point by 20 meters or minus 20 meters. Lastly, we know gravity. It's 9.8 meters per second squared. And what do we want to find? We want to find time. All right, now we're going to grab the one equation that comes up when we use this quadratic formula. It's always going to be this one, where we have y final equals y initial plus VO in the y direction times t minus 1/2 gt squared. Notice here we have a squared and a regular old t and without a t. And that's why this maps onto our quadratic formula. Okay, so let's go ahead and plug in what we know. Our y final is minus 20. Our y initial is 0. Plus our velocity initial in the y direction. We're going to go ahead and just write that as 14.3 from now on. But remember, that's the number we want to keep the whole thing of in our calculator. Minus 1/2 times our gravity, which is 9.8 t squared. And now what we'll do is we'll start to simplify this. Okay, and what that means is we're going to try to set it equal to 0 and kind of simplify all our terms. What we'll do is we'll move everything over here onto the left-hand side so that we get this all equal to 0. Okay, let's try that. Well, what we'll do is we'll subtract 14.3 from both sides, and we'll add 1/2 times 9.8 t squared to both sides. We could actually go either directions here. If you wanted to get everything to the right, that would be fine, or everything to the left is fine. Either one is great. So when we do 1/2 times 9.8, we're going to get out just 4.9. So we'll write 4.9 times t squared. That's this term that we've added over. And then we'll have minus 14.3 t, and then our last term minus 20, all equals to 0. So this minus 20 just stayed there and hung out on the left-hand side. Notice that this is very much like our quadratic formula, where we have a x squared plus bx plus c equals 0. So in this case, we want to decide what a, b, and c are equal to so that we can solve for, in this case, time. So though the quadratic formula typically has x sitting there, we can actually solve for it in terms of time. So let's get rid of that x and just put a t there to make it totally clear what we're doing here. T squared and t. Okay, so t's can be there as well. What is a equal to? Well, a is just the number in front of t squared, which is 4.9. So notice a is determined by which component it's squared with. If it's with that squared component, we know it's 4.9. Okay, what about b? b is what's in front of t. And in this case, it has to be minus 14.3. So it's minus 14.3. Lastly, we have c, which is going to be minus 20. Okay, so we have identified our a, b, and c, and now we're ready to grab our quadratic formula, which, remember, tells us that our two roots are equal to negative b plus or minus square root. You can sing it if you want. B squared minus 4ac all over 2a. And so what we'll get there when we plug in negative b, so b was minus 14.3. When we take the negative of it, we'll get 14.3 plus or minus square root. And then we're going to have that same b, 14.3 squared, minus 4 times our a, which was 4.9, times our c, which is minus 20. And that's all under that radical. All divided by 2a, which is 2 times 4.9. You can see that the quadratic formula takes a little extra effort to use. When we start to simplify at this point, what I like to do is go ahead and just rewrite the solution here, only simplifying everything under the radical. So I'm going to take 14.3, I'm going to square it, I'm going to subtract 4 times 4.4 times minus 20. And what that'll give us is still the 14.3 up front, plus or minus, and now when we plug all of that into our calculator, we're going to get 24.24 and some decimals, which you should again store, all divided by our 2 times 4.4, which is 9.8. That gives us two solutions. When we add everything together, when I do 14.3 plus 24.45, I'm going to get 3.96. When I do 14.3 minus 24.45, I'll get minus 1.03. Both of these are seconds. So these are the two possible time solutions we have where that rock is going to be 20 meters below our initial starting height. Which one should we take? Well, clearly this minus 1.031 represents the time when it would have been below the initial point on the left-hand side. And minus time doesn't make much sense anyways, right? So we're going to go with that positive answer of 3.96 seconds. So that's a lot, but that's how we can use the quadratic formula to solve projectile motion problems. So we found that it took 3.96 seconds for that rock to get 20 meters below its initial starting point using that quadratic formula. Let's review what we've learned. We've used parabolas to explain projectile motion. We saw that that was the mathematical function, though an upside down parabola, that tracked with our object. Then we introduced the quadratic equation, which allows us to solve for what are called the zeros of our parabola. And lastly, we practiced solving projectile motion problems with that quadratic equation. And it let us figure out how much time it took for that rock to fall out of the volcano.
Hey, hey.